Have you ever looked up at the night sky, on a clear, dark night, far away from the city lights, and wondered, truly pondered, with a sense of awe and perhaps a touch of bewilderment, why is there something rather than nothing? It's a question that has plagued philosophers and scientists for centuries. Why does existence itself exist? Why does the universe exist at all? What is the fundamental reason for its being, its vastness, its intricate complexity? Is there a purpose, a cause, or is it all just a cosmic accident? Today, science offers a mind-bending answer, an answer that challenges our deepest intuitions and forces us to reconsider what we think we know about reality. Everything we see, every star, every galaxy, every planet, and even ourselves, may have emerged from what we call nothing, from a state of absolute emptiness. This isn't magic, no supernatural intervention or divine creation, but the result of the bizarre laws of physics, the strange and counterintuitive rules that govern the universe at its most fundamental level. At the quantum level, the realm where particles can be in multiple places at once, and where the very act of observation changes reality. We'll explore the quantum vacuum. This isn't just empty space as we perceive it. A concept that redefines emptiness itself. It's a place teeming with potential, a hidden reservoir of energy and possibility. What we think of as nothing, that absence of everything, is actually a dynamic field, a roiling sea of virtual particles constantly popping in and out of existence, brimming with potential energy. This is the story of how the universe could arise from the void, a spontaneous creation from seemingly nothing, connecting the tiniest scales, the subatomic world of quarks and leptons, to the grandest cosmic structures, the vast web of galaxies that stretches across the observable universe. So buckle up. Prepare for a journey to the very edge of knowledge. We're about to dive into the heart of the void, into the deepest, darkest recesses of existence, and discover how physics might create a universe from nothing, how the seemingly impossible became reality. Prepare to have your concept of emptiness turned upside down, to question everything you thought you knew about the origin of the universe. Let's begin our journey into the ultimate cosmic mystery, a journey that will challenge your mind and expand your understanding of the universe. Imagine an empty box, a simple, unassuming container. What does it hold? At first glance, the answer seems obvious: nothing. But what does nothing truly mean? You remove every atom, every photon, every single particle of matter and light. You create a void, a space devoid of anything we can readily perceive, absolute emptiness, right? A perfect, undisturbed vacuum, a true representation of nothingness. For centuries, this was nothing, a perfect void, the ultimate absence. Scientists and philosophers alike considered it the baseline, the 0 point. But at the quantum level, our understanding of nothing takes a dramatic turn. Emptiness doesn't exist. The seemingly empty void is far from inactive. Even after removing everything, all the matter and all the light, the box is still buzzing with hidden energy, a subtle yet powerful force at play, the quantum vacuum. This isn't just empty space, it's a dynamic arena of activity. This vacuum is the universe's baseline energy, the fundamental level of energy that permeates all of existence, far from quiet. It's a constant hum, a subtle vibration that underlies everything. Think of a calm lake, a serene and tranquil body of water, seemingly still, a picture of perfect stillness. But at the microscopic level, it's a frenzy of motion. Molecules are constantly colliding, vibrating, and exchanging energy. The quantum vacuum is like that, a deceptive appearance of stillness hiding immense activity. Space looks empty, a vast and desolate expanse, but at the tiniest scales, far beyond what our eyes can perceive, it's a roiling sea of energy, a chaotic dance of quantum fluctuations. This is due to the Heisenberg uncertainty principle, a cornerstone of quantum mechanics, which says you can't know both energy and time exactly. There's an inherent limit to how precisely we can measure these two fundamental properties. That uncertainty allows for tiny, spontaneous, fleeting energy fluctuations everywhere, popping in and out of existence in the blink of an eye. Even in a perfect vacuum, these fluctuations persist. These fluctuations mean that nothing, as we traditionally understand it, is never truly empty. It's always teeming with potential, with the possibility of something arising from seemingly nothing. Emptiness, it turns out, upon closer inspection, is just an illusion, a trick of perspective. The quantum vacuum is, in reality, the restless foundation of reality, the very fabric of space and time. It's the stage on which the universe's story begins, the canvas upon which all of existence is painted. The next step, the crucial question that arises from this understanding: what do these fluctuations actually do? How do they shape the universe we observe? Let's find out. Let's delve deeper into the mysteries of the quantum vacuum. Thanks to the bizarre rules of quantum mechanics, specifically quantum fluctuations, something truly extraordinary happens even in the emptiest vacuum. What seems like nothingness is actually a hotbed of activity. At the heart of this phenomenon is the fundamental principle that energy and mass are interchangeable, elegantly expressed by Einstein's famous equation, E equals mc squared. This equation reveals a profound connection. Because of this, tiny, fleeting bursts of energy, popping up spontaneously, can briefly materialize into pairs of particles and their corresponding antiparticles, creating a spectacle of creation and annihilation. These ephemeral entities are known as virtual particles. They are not directly observable in the traditional sense, but their effects are very real. These particle pairs pop into existence seemingly from nowhere, borrowing energy from the quantum vacuum, then almost immediately annihilate each other and vanish, disappearing in a flash of energy, all happening in an incredibly short time span. The vacuum, far from being empty, is constantly loaning energy on very short terms. For these fleeting particles, which always scrupulously pay it back before they disappear, it's a cosmic balancing act. To visualize this, imagine the vacuum not as empty space but as a deep, dark ocean, where countless invisible bubbles are constantly forming and vanishing in its hidden depths, a chaotic dance of creation and destruction. This seething, bubbling activity is what we call quantum foam, and it's not confined to distant corners of the universe. It is everywhere, permeating all of reality, even inside you within the very atoms that make up your being. And the existence of virtual particles is not just a theoretical construct or a mathematical curiosity. We've directly measured their subtle but undeniable effects in laboratory experiments. A prime example is the Casimir effect, a bizarre phenomenon, which demonstrates that virtual particles, despite their fleeting existence, exert real, measurable forces on the world around us, subtly pushing metal plates together when they are placed in close proximity within a vacuum. This seemingly simple experiment provides compelling evidence that the vacuum is not an empty void, but rather a dynamic and energetic place, teeming with activity. The quantum world, at its most fundamental level, is never truly still or at rest. It's a constant flux of creation and annihilation. Even what we perceive as nothing, the absence of everything, is actually alive with potential, brimming with the seeds of existence. But could these seemingly insignificant tiny quantum fluctuations ever scale up to create something far bigger and more enduring? That's where our story takes a dramatic turn, venturing into the vast expanse of the cosmos and exploring the origins of everything we know. Picture the quantum vacuum as a deep ocean, full of potential energy. Normally, only tiny bubbles, virtual particles, appear and vanish. But what if, by chance, a much larger bubble forms, a bubble of space-time itself? This is the idea behind cosmic inflation. A bubble of false vacuum rapidly expands, stretching space-time at incredible speed. This inflationary bubble becomes a self-sustaining pocket universe. When inflation ends, the bubble's energy is released, transforming into a hot soup of particles and radiation. This is the Big Bang, not the beginning of everything, but the moment our universe burst into existence. The universe is the aftermath of a giant quantum bubble that didn't collapse. From a quantum ocean, a cosmos is born. The Big Bang may not have been the ultimate beginning. Instead, it could be the result of a rare quantum fluctuation in the vacuum. Most fluctuations are tiny and fleeting, but given enough time, even the most improbable event, a universe-sized bubble, can happen. This bubble, powered by repulsive gravity, inflates rapidly. Inflation is the engine that turns a microscopic fluctuation into a vast universe. When inflation ends, the energy transforms into matter and radiation, the Big Bang. The universe is now hot, dense, and ready to evolve. In this view, our cosmos is the product of a lucky accident in the void. A quantum seed, inflationary growth, and a Big Bang, the recipe for everything. The universe is the grand result of a single, fortunate fluctuation. From the void, reality blossoms. But doesn't creating a universe from nothing break the law of conservation of energy? Surprisingly, the answer may be no. The universe contains positive energy, matter and radiation, and negative energy, gravity. Gravity's pull is like a cosmic debt, balancing out the positive energy of everything we see. According to inflationary theory, these energies may perfectly cancel, making the universe's total energy zero. The universe is a cosmic equation. Positive matter plus negative gravity equals nothing. So the universe didn't violate any laws, it just split zero into two parts. A quantum fluctuation can create a universe as long as the books balance. Our cosmos may be the ultimate free lunch, something from nothing with no net cost. The grandest creation paid for by perfect balance. The universe is a zero-sum miracle, and the evidence is written across the sky. This theory isn't just speculation, it's supported by cosmic evidence. The cosmic microwave background, or CMB, is the afterglow of the Big Bang. Its uniformity across the sky is a puzzle, but inflation explains it. The universe was stretched from a tiny smooth patch. Tiny temperature ripples in the CMB are the fossilized imprints of quantum fluctuations, magnified by inflation. These ripples became the seeds for galaxies and cosmic structure. When we map the CMB, we're seeing the echo of the universe's quantum birth. The largest structures in the cosmos began as the smallest jitters in the vacuum. The quantum world shaped the universe we see. The evidence for a quantum origin is all around us. Cosmic inflation leads to an even wilder idea, the multiverse. If a quantum fluctuation created our universe, why not others? Many models suggest inflation never fully stops, spawning endless bubble universes in a vast cosmic foam. Each bubble is a separate universe, possibly with different physical laws. Most would be inhospitable to life, but we exist in one where the conditions are just right. This is the anthropic principle. We observe a universe suited for us because we couldn't exist in any other. Our universe may be just one of countless bubbles in an infinite sea. The multiverse is speculative, but it's a natural consequence of eternal inflation. We may never see these other universes, but their possibility expands our cosmic perspective. The quantum vacuum could be the birthplace of infinite realities. We've journeyed from the idea of an empty box to the possibility of a multiverse. The quantum vacuum is not empty, but a restless sea of potential. A single quantum fluctuation, magnified by inflation, could create a universe. The total energy may be zero, matter and gravity in perfect balance. The evidence is written in the oldest light, the CMB, and in the structure of the cosmos itself. When you look at the night sky, you're seeing the legacy of a quantum whisper. The universe may not have come from absolute nothing, but from a quantum nothing, the source of all potential. The cosmos is stranger, more beautiful, and more magnificent than we ever imagined.